Okay, so in the last class, we started talking about how we can reduce the problem of overfitting in machine learning. And believe me that every machine learning methods to be successful, the only difference that you have to make with the other unsuccessful solution is one is regularization and other is the validation. How you use your training set in order to validate something to get better performance at the end, and how you can regularize so that you do not fit noise but fit the actual data properly. So remember the example of movie rating that we gave, and that was a Netflix challenge for $1 million of a prize, and the winning solution used regularization to the best way possible. So it says that without the unconstrained fitting, we go into fit for a overfit, because in unconstrained fitting we also try to fit the noises. Then we move to a constraint fit where the constraint was imposed in terms of a soft order constraint rather than a hard constraint, where we mentioned that the sum of the weight square should be less than a budget. And we found that to have this to be minimized within a budget, then actually this WTW is equal to C is a circle where my weight will be at the edge of it to become more close to W lin, which is the actual solution which minimizes E in. But now your minimization criteria becomes with the regularization this augmented error, not only E in, but also someone pulls you down. So you need to produce that inside the equation. And that's what the KKT theorem also give us. With a constant which is quadratic, we can push into the equation and can solve this without any constant, or maybe with lambda greater than equal to 0, which is a just a kind of a constant which we need for the regularizer. Now we have seen that it gives a drastic improve in the performance where we are fitting the same fourth order polynomial here, fifth order polynomial here for this fourth order polynomial for these 5 points and doing an overfit. Then gradually when we give a little lambda, we get a good regularization behavior. But the curse is that if you are too tempted to make your lambda higher, then what it would mean that it will try to pull this circle down towards the center, which is W becoming 0 at the end if your lambda is infinite. So therefore, it again sacrifices your performance by smoothing the curve too much than expected and leads to underfitting. So we have so therefore, what is the best regularizer? It depends upon the choice of hypothesis that you make, that is the weights that you get with respect to the lambda that you have to produce. So now, as you can see that the augmented error is not only the in-sample error, but also it comes from the regularization impact that you made. So obviously the choice of this regularizer, which depends upon lambda h and this term of the weight that you make due to the constant you impose, that is C, and the boundary that you impose on the weights. So this is a heuristic choice, and we often have seen that smooth curves with simple h functions are basically more better regularizing performing as a better regularizer than the others, and we sometimes call it as an Occam razor, that is the simplest hypothesis fits better. And the popular thing we also have seen in case of stochastic gradient descent, whereas the earlier cases we discussed about the linear regression one-step learning. But in stochastic gradient descent, we see that the weight is now not only just have a gradient of E in to be reduced, but also there is a small decay depending on the lambda that you produce and the learning rate. There is a small decay that pulls the weight down inside this realm of the boundary C, so that it does not shoots up here and there, and therefore you always try to converge into a good smooth weight for the curve. And we have also seen for the neural networks this weight W is a little bit of complex, because it now has from the ith layer to the jth layer, and the number of layers you sum over it and do that. And we have also seen that why this smooth curve we are emphasizing on, because we see that the weight decay is a better parameter to experiment with while regularization rather than weight growth. Because weight growth meaning that I will only keep the higher order terms, not the lower order terms. And keeping higher order terms means that when you keep the higher order terms, it means that your function is a higher order polynomial, which may not be always smooth, and therefore you sacrifice the smoothness aspect of it, which we thought that simple smooth functions will not fit deterministic as well as stochastic noise as well. Just excuse me once. So that's why we thought that this regularization is a very good weapon for us to better fit the final learning that we can get out of it. And there are three things that we need to foresee here also is what is the choice of lambda that we make, and what do we do about how we perform in the out of sample. So there is no out of sample available in our hand to as per se, because we are given with an in sample and then we have to perform the training over that in sample data and then come up with a particular hypothesis that is our final outcome. So how can we reason about out of sample? And this generalization is based on a very pessimistic Hobding inequality based measure, which we have seen that it also has a budget for the overfit, but it doesn't predict it. It allows overfitting, but it does not predict it. So in today's lecture, we will be mostly concentrating on the validation aspect. You all used it in your projects, but theoretically, what does it mean? We will try to go through that. So let us start. First of all, if you look at so our equation of E out given a hypothesis H is basically E in. So we can only estimate this part. Then what we did as part of a generalization, we allow certain penalty. So this penalty is meaning that this is your E out, for example, and then you allow this kind of a buffer over which, depending on the E in this is your penalty that you allow over the E out, plus minus of that you may say, a penalty that you allow through your E in, you will visualize E out within this penalty. Therefore, there an out of sample point could be anywhere within this, and you allow this penalty as your generalization penalty bound. Now, if you look at the role of a regularizer, so this penalty, or just one more point, this penalty could be due to overfitting. This penalty could be due to model selection. So you select a decision tree model, which is a very bad fit. Maybe a neural network could have been a good. So this penalty could also be due to the different kind of noise that we have seen, either in the stochastic domain or in the deterministic domain. We cannot fit well. So therefore, this penalty has various places from where it can come from. Now, the role of regularization is just to estimate this quantity, because now see, regularization deals with an augmented error. In order to estimate E out H, it deals with an augmented error, and what it does is that augmented error is nothing but it tries to have a regularization of that. And regularization, obviously, you can see that it tries to deal with this penalty by estimating or coming close towards the reduction in the penalty by this kind, regularizing this estimate. Whereas if you look at the validation, the other thought would be that why bother about only in sample? The other thought could be that why not I reduce the cut down or reduce the target itself. By reducing the target mean, instead of reducing this penalty in sample plus penalty, this augmented thing, I directly try to foresee what my E out H is and try to reduce it so that my in sample error tracks it very well. Reduce or increase depending on this parameter. I am thinking only as a plus penalty. So I say that if I reduce H, then in sample error will track out of sample error very well. So ultimately, in our learning, our goal is this. So this is our goal. So two ways to do it: reduce the penalty, reduce the outage. Regularization or any learning kind of a method, if you go better and better model selection regularization, it tries to cut down through the penalty and thereby making E out and E in H both are same. Whereas validation, try to look into the data and try to estimate your model, your learned hypothesis over that data and try to cut down the E out. It seems too far to be true because we are only given with a set of points in our hand. We do not know what is the out of sample. But here is also a catch on it, because we are only given the data sets. So what if we separate out a certain portion of the data sets and think that it may be the out of sample it may be act as a proxy in the out of sample. So we will see in a minute. Before that, let us also clear up one particular concept is that suppose I am given an out of sample point. So the role of validation rather, suppose I am given an out of sample point which is x, y. Now, what I try to do in validation, I try to estimate the error first of all. So my error is basically over the point x, which is my hypothesis give, and the actual output that the point produces. This will be my error. Now, you can see that this is, we have already seen two different types of errors in our courses. One is the squared error we performed in linear regression. Another thing is that if it is a +1 or -1 kind of a classification, we see a binary error, whether it matches or it doesn't match. So inside formula is true or false. Depending on that, we classify the error. But when you see only one point out of sample, then what does it mean to tell about E out age? So with respect to a point in the sample, if we generalize it, we have also seen that we generalize it over with respect to all the points that we will see and the expected error with respect to that point. That is how we formulate mathematically the out of sample error with respect to the hypothesis H. Obviously, if you only look at a point and you try to have an expected out of sample error, there could be a variance because your E out could be this and you could be within this region. Somewhere you will pick up. So you may be picking up with respect to this point, you may be picking up your E out. So therefore, there is a variance in the E out space depending on the distribution of the point, so that picking up a point, you can pick up any of these E outs in this space. So which means that the variance of this error also has a significant impact in whatever we produce as this out of sample performance. And let us say it's a constant, and I am assuming sigma square to be on a more colloquial side. Let the variance be sigma square so that my standard deviation will be sigma. So this is how we interpret about validation out of sample performance over only one point. So this is how we do over only one point. Now, if you try to move from one point to a full validation set, that means a set of points. So let us see what does the benefit that we get instead of only considering an arbitrary from the distribution, pick up an arbitrary point. I compute the error and take the expectation of that. That will give me E out, but there is a chance of variance on that because the distribution, depending on the distribution, your point will give some value of E out, which may be within this range. So what if we pick up a set of points? By set of points, I mean I give you a validation set of k points. Then again, if you see that what will be my performance of validation in this particular set of points, so that is E validation if I choose an hypothesis H, is nothing but, as you can see, it's the average of the errors that I make in each of these k points. So each of these k points, the average of the error I make, it's my validation error. So now if I go for again computing the expectation of that, so expectation of this is nothing but, you see, expectation of 1 by k sum, and the expectation will come inside, and we know expectation over each point of this is E out H. So k times E out of H by k is nothing but it's just your E out H. So what does it mean is that it will also, if you take k points instead of 1 points, the expected validation error will also point to the expected out of sample error in a same way. But the improvement that we will get in variance is the fact that if I now try to compute eval of H, now see here, if you take the variance, all the cross terms will also come into picture. So there will be k square number of total terms each k equal to 1, small k equal to 1 to capital K in both directions, and there will be a cross variances. But the good thing is that only diagonal cases where this k matches in the cross terms are only be in my picture. The other terms will cancel out as for the statistical variance quantity. However, there are total k square number of terms, therefore my average will still be over k square. But the thing is that since the cross term cancels out in this, so this will be h xk yk, and since my cross term cancels out, this is a variance I know by sigma square, and I only have this k number of terms to do with it. So therefore, this will be like this. So then what do we make improved impact upon is the fact that now my variance is not sigma square anymore. I mean, if you look practically in a common sense manner, it also makes sense, because instead of estimating E out with respect to an arbitrary one point you pick up, there is a more chance that you land up in a bad zone not estimating E out here. But instead, if in from the distribution X you pick up k number of points and try to estimate, obviously your variations will be less, because there are the more chances of accurately trying to pitch in or trying to look for E out increases. So that's the overall deal, and therefore you will see that with respect to k points, if I have, effectively my out of sample will become this in sample, and this, assuming sigma to be constant, this is nothing but this is plus minus order of 1 by root k, because the standard deviation of the error is 1 by root k, is a factor of 1 by root k. So that, as you can assume, that the more number of k is given to me as validation points, the better in sample error tracks the out of sample, which is my overall goal in learning. So validation definitely plays a role in order to push the in sample barrier towards the out of sample and making it almost closer. Clear this point, why we need a validation and what is its impact?
Yes, sir.
Okay, so 2 points from here is that the more the number of sets, one point is validation obviously makes an impact to move this relationship so that my learning is good. The second impact is that the more the number of validation set, the better approximation towards the E out that I can make from the in sample error. So, but the challenge that we have in our hand is that we are only given with the data sets. There is, if somebody gives me on top of my data set some ground truth validation set, then my job is easier. But instead, what is given to us is a data set containing, let's say, n points, x1 y1 up to xn yn. Now, depending on whatever is being produced, whatever is being given to us, this is only in our hand. So we break it down into two sets. One is k points, and we call it as a validation set, and the other is of n minus k points, and we call it as a train set. That is for training. So I will use this set for training, and I will use this set for validation. That's the deal. And if I rewrite the previous equation theoretically, that I have found out that my E out will be tracked by my E in very well if my k is pretty large. That's what I have seen. And if you try to plot a graph of about the k estimates and E out and E in, you will look this kind of a behavior. So obviously this is your expected error line. This is your in sample. As you know, it grows like this, and your out of sample, somewhere down the line here, it comes like this. Now you see, this is the known curve for us, where we know this is my E out and this is my E in. However, my training point now is of n minus k. So this side now is n minus k because that's the only number of points that is given to me for the training. This side is error. So as you can see, if we have small k, what will happen if we have small k, then this estimate is bad. That means if we have small k, we are in the chance that we are in here. That means we will track E out well. However, the estimate that I will give will be always bad. That means from E in, so E in plus some generalization error will be E out, and I am always will be in the boundary of the generalization error in terms of my estimate, nowhere near the E out. Whereas if I have, so if I have a small k, I have a bad estimate. Remember, this part is hidden from you. You do not know it. You can only estimate this and predict what will be this one. Therefore, if there is small k, so this part will be huge and hence your prediction will be bad. Though you are in the realms of good generalization, but still the boundary of the generalization may be big enough so that your estimate could be bad. That's what I want to point out. Now, what happens if you have a large k? Large k means your k grows this side, right? Your k grows this side because n minus k grows this side. That means k grows this side. Large k means what? That whatever you predict in sample will exactly follow very much close to out of sample. Because if you have large k, this term vanishes. However, you see, if you are here, your out of sample is this. If you are here, your out of sample is this. If you are here, your out of sample is this. Now, more and more you make your k large, the problem becomes you give a perfect estimate over a very bad model. Did you get the point? You give a perfect estimate that I have very less training data. Suppose here I have only 2 training data. I fit a linear line on that, and that's my estimate. And I will say that's a higher. I have a best confidence that this estimate is very good. But the role of learning is not to provide a bad estimate with a very good approximated quantity that it is from the in sample from the training data what you have given. My estimate is bad, but the estimate will match the out of sample. That doesn't make sense because your also job is to reduce the out of sample error as well. So there is a dilemma, as you can see. So one way to cater to this dilemma is that let us do it in this way. As of now, we understood that my D I separated out with D train union D validation. And we know that my D is of n points, D train is of n minus k points, and this is of k points. So the choice of k, I am in a dilemma. So what I will do is that from the D, when I keep a little bit of data for D train, so after training to this data, I get a hypothesis, I tell it G minus because it's on a less amount of data than D has. So I have a minus superscript on it. So this I detrain on n minus k amount of data. Similarly, with this D, I validate on k amount of data because that is the only available with out of thing. And I validate this G over this k amount of data, validate it, and produce a validation error. And produce a validation error on that. Validation error means this one, the whole thing. What I do next is that I put this k data inside this pot and try to find out an hypothesis G from the n training points. So deal is simple. N minus k I will use to train, get my hypothesis G bar, G minus. K I will evaluate this hypothesis and give you eval h, which I assume to be tracking to E out h better because the higher the k, it is better. But higher the k, lesser the n. So you go to this side in the curve, the initial side, your E out is bad. So I want to give my customer a good hypothesis as well as a good estimation of my hypothesis. So I give G and also I give this one. But the problem is that G has nothing to e-validate because I have no data to validate G, but I have validated this one. If K is large, then the discrepancy between G and whatever you provide as the proxy to be E out will be higher. So my claim is that if K is large, then G eventually does not track whatever I mention here. I will provide this as my final hypothesis and this as my estimation. This each other doesn't track well because if K is higher. So there is no theoretical proof here, but people have used either n by 5 amount of data for validation or n by 6 something, and they have seen that the results are almost good for they can give good hypothesis and also they can give a good estimate as well. But the role of the game is that you validate by breakup and then put both the data in the same pot and try to find out your G. That caters to the part that I do not go this side, rather I find something from here. And since I get a K to be to be a little bit higher, so maybe this estimate I give with this E out of the hypothesis. So there is a discrepancy, but to reduce the discrepancy, people tend to choose n by 5 or n by 6 as the value of K. For the time being, let us take it for granted. Later, I will dig down more on it. Okay, the initial strategy of validation is clear. Yes.
Yes, sir, but I have a doubt for with respect to the condition of large K and that point.
Yeah.
It is
Which
not clear for me.
this curve?
The yellow color written with this curve, when we assume the K is large, then there is a dilemma na that part.
The dilemma is that see, small k means your in sample what performance will not track out of sample performance because there is a relation of 1 by root k. So small k means
Hmm.
this penalty would be huge. So your in sample whatever you perform will not track
Estimation
out
is
of
bad.
sample. Bad. Large k
Hmm.
means your estimation is I mean inch perfect, right?
Obviously, E out is equal to E in here.
Almost, almost. If k is
Hmm.
infinite, it is equal to. Now, if k is large, you are in the initial part of this curve, which means your E out is very bad. That means the hypothesis that you supply to the customer is even very bad hypothesis. It is not even close to the expected hypothesis. It is not making an expected error. It is making a huge error in the data set. So you are giving a bad food and
Yes.
telling that I have cooked it with full confidence. Or you are giving a good food
Hmm.
but telling it that my confidence how it is bad. That's the difference. That's the
Hmm.
dilemma.
Hmm. Okay, sir, I understand.
And now see that now the second point is that why do we call it as a validation set? And here is a very intriguing notion we will try to understand here. See what happens is that you are given, so why not it's a test set as well. One of the reason could be that I put it back and take it for training, so it's a little bit contaminated. I mean I see it for validation and then I put it back and take it for training. So earlier when I use for training and testing, test set is totally uncontaminated and it's a pure unbiased set. Where is the bias coming in from here? Let us try to understand. Remember the early stopping curve when we do. So the early stopping curve says that suppose this is my E in, this is my E out, and after a certain point it grows. And looking into the behavior, I somehow stopped here. How do I stop? I stop by some validation approach. I stopped by separating out some data to be k and found out that after a certain point, I found out that that k value is giving a bad estimate suddenly, and I stopped. But now see, when I have a choice of stopping, so let's say I have two hypotheses, H1, H2. Where is the contamination coming? Let us try to understand. And let us say E out of H1 is the same as the out of sample performance of H2 is equal to half, 0.5. And let's say the error that H1 makes is E1 and the error that H2 makes is E2. This is a uniform distribution of 0 to 1. It makes an uniform distributed error value with H1 and H2, two hypotheses like that. Now, upon validation, so what it means that upon validation, which one you will pick is basically I will pick whichever gives me minimum error in those points, meaning that whether I will stop here or move here is depending upon whether my hypothesis is giving till which point the minimum, right? The hypothesis could be same at different number of training. The hypothesis could be different model itself. But my stopping criteria would be whichever point I find it the minimum error I am making. Now see here, since you have a little bit of set in your hand to validate and find out the minimum error, that is k number of elements beforehand you keep aside. Now here you have an optimistic bias. The optimistic, why I call it as an optimistic bias instead of no bias at all, because of the following fact that your optimism says the expected error will be less than 0.5, because if my E out H1, E out H2 is half and I took a uniform distribution from 0 to 1, I have an optimism that minimum of picking E1 and E2 will land me to an expected error of less than 0.05. That's the optimism. And I got this optimism by looking into the validation with respect to k values. So that's why I call this one is an optimistic set, which used to be validating my data and trying to reach to an optimistic view of error, which may be less than 0.5, though the actual error on each of the hypothesis may be equal to 0.5 or something, maybe more than 0.5. So in summary, in very colloquial language, we can say that when we separate out a little bit of data set as a validation, as set to verify our estimation, we have an optimism that verification will pick up lesser number of errors happen among the answers that I will produce and then stop there. So due to that optimism, this data set is a little contaminated, I would say, not fully contaminated, because I am again putting it back to make the final hypothesis and all, but this contamination makes an optimistic bias going on because I have an optimism to stop here. That's what I want to point out, that if we do not stop and go in reducing E out till the n number of data points that is given to us, it's totally unbiased error minimizations and I give you the answer. Now I have an optimism to stop early with respect to the validation point, and that's why I do not call it as a test point but a validation point. Depending on test point is unbiased, validation point has a little optimistic bias. That's it. We will formally state these things again in the next slide. So let us say that what we are trying to do. Suppose we are given with M model. Now let us try to dig down to understand the validation problem into more details. Suppose we are given N models, H1, H2, HM. As we always do, there are many models to choose from, and we are given a set T train to train this model. Now, this model could be absolutely generic in a meaning that someone could be decision tree, someone could be support vector machine, someone could be neural networks, someone could be a polynomial of order 2, someone could be a polynomial of order 5, someone could be a polynomial of order 10. Even someone could be same polynomial, all of them could be same polynomial with a regularization lambda is 0.001, regularization lambda is 0.01, Regularization lambda is 1. So these are my sets of models, and I want to pick the best hypothesis from these models given to me. I have the training data and I have the validation data. I have a training data set and I have a validation data set. So what I will do first, at the first step, I will, with respect to my training data, from this, I will try to pick up the best hypothesis in this set. From this, I will try to pick up the best hypothesis in this set, and so on. Up to this, I will try to pick up the best hypothesis with respect to only the training data that is available to me. Now, I need to validate. To validate, I mean that what I will do, each of the hypotheses will produce certain errors in the validation set. Right? Simple. That each of the validation set I separated out. So this is with n minus k points and this is with k points. Each of them will produce certain errors. Now, in this step, what I do with the validation, that depending on that, I pick best. That is the least error that is made by which hypothesis. Now, the second step, as I do that, I put all these data in the same pot, make the full data set, and then train the data set. Since I know and I have picked the best, suppose it is EM, I make it as a star, it is the best one. And suppose it is from some hypothesis H small m star. So I train the data with respect to only that hypothesis where the error is minimized, where the validation says that picking up a hypothesis from that set minimizes my error, and therefore I give my final hypothesis. This is an extended way of looking into the validation. Earlier, what I did it for one model, but effectively, when in your project, if you see that suppose you are only given data points to fit in, what you will do? You will not, I mentioned you that do it in decision tree learning, do it in this linear model. So you are doing it that way. But effectively, in a real life problem, you have to select your model in a different or in a variety possible way. You do not know which model will fit. So you will separate some data for training, some data for test validation. And then what you do, each of the model, you will try to see which is the best hypothesis I can pick up and try to validate that wherever the error becomes minimum. From that set, you will try to train and get out the final hypothesis. Remember that this may not be GM minus because I am again using the whole set to take out my final hypothesis. GM minus can be different and this can be different. Maybe with all the data, I get a different hypothesis than that was best with only the training data. This K data may matter. You never know. So this is my game. So this is my validation approach. What I told. Approach is clear.
Yes, sir.
Okay. So when you do that, you use, I mean, what I am doing is that I am just digging the theory. You have already used it in your project. I will tell you the name later. Then what will happen, you see that suppose if I run an experiment, that's just a illustration of experiment in terms of a graph. Suppose I have two models, that is second order polynomial and a fifth order polynomial. Instead of this m, I said I have two models to select from. And what I found is that this is my validation set size k, this side, and again this side is expected error. So when I plot it, I found that one is like this, which is E out of performance for GM minus, that the GM minus you picked as the best one. And this is like this, what will be your eval for the GM minus. See, I picked up a hypothesis GM minus, which gives me less number of this as my final set, and then I train it and give you this as my answer with eval GM minus as the estimation. I hope it is clear to you, because the estimation I can only get with the validation. So estimation will be with respect to GM minus. My final answer is maybe different. Agreed?
Yes, sir.
Yes, sir.
So therefore, what I now need to guarantee is that how close it is. I will experiment how close it is with respect to out of sample by actually applying it in a practical field. So I have two questions for you. Tell me, first of all, why this curve grows like this upwards, the orange curve, and why the two curves meet. Question number one, why this curve grows like this? E out.
So as k is increasing, out of sample example is also increasing. So it is same to
No,
validation set is
this
same
side is
to.
this side is k. This side is k. See, if this side is k, this side is your number of training, right? This side, if this side k increase, this side n minus k increase, the other way. Isn't
Yes,
it
sir.
my out of sample curve? If you look from the right to left side, is it my out of sample curve looks like this? Look at here. Your out of sample curve is this one. It looks like this with respect to n. I just flipped it, mirror image, because my n now grows this side. Why these two curves meet? It's very simple. Higher the k, the better chance my validation set will estimate E out properly. That's what I just discussed with respect to this equation. See, now I am with my validation set, because these E in will be with respect to validation set at the second iteration, right? At the second iteration, to be more specific with respect to validation, I have these as my selected finalist. These are my selected finalist from which I am choosing the least error making hypothesis, and that set as to train in the final way. So therefore, you can easily understand this will give rise to E out GM minus. You can again apply the back to Hobding and VC inequality with this set as your in sample set, is nothing but now my in sample I am writing it E validation GM, let's say it's from M star set GM star minus, plus the Hobding inequality will give you nothing but if there are m number of models, it is proportional to this instead of 1 by root k. I mean, it's a standard result. You can just use the Hobding inequality and can make it. Or to be more specific, this is root 1 by 2k ln 2m by delta with 1 minus delta probability of or confidence. This is to be more accurate. If you try to estimate, it will be this one. And as you can understand, it has a similar notion following from the Hobding inequality. This ln and all, we have already explored this one when we have E out and E in. The only things to remember here is that E in is now my eval, because at the second part, validation set has to take the G's as its model and try to finalize a G, or the estimate to be finalized based on this G, where we do early stopping and all that. Right? Agreed?
Yes, sir.
Okay. So if this is the case, so let us summarize whatever we did. We have an E in that we did in the first iteration with the n minus k, and then we have an eval that we come up across this, and then we have an E out. Right? So the dilemma is this, that we are trying to estimate E out of G with respect to E out of G minus. That is, whatever we can train with k points separated out will be our EG minus, and that we get an estimate with the validation set with respect to the validation G minuses that we have in our hand. Now, as you can see here, this inequality depends on the k in the denominator. So large k is good for this inequality to happen. Whereas this is the final hypothesis that I get, and this is the with respect to only the training data. So this is mostly if we have small k, then this will result. Did you get the dilemma again in the formal notion here? G is the final hypothesis that I want to give from n training data. G minus is the hypothesis I compute from n minus k training data, with separating out k data as my validation set. Therefore, this will equate if my k is small, whereas this to this, the validation, this should equate because my validation will equate E out G minus, as you can see by the equation, this one. So k is in the denominator. So the large k, this will equate. So I have to have k to be small. I have to have k to be large. New mathematics will come out. Okay. So that's why rule of thumb. There is no solution. Rule of thumb is n by 5 to take k as n by 5. However, if you understood the theory, and I mean, even if you do not understood the theory, that's not a problem. If you understood this example, that will be absolutely clear for a few things. What I will do for this is that I will let me introduce a little bit of cheating on that. So what I will do in this, suppose I am given n points, x1, y1 as the data set. Somewhere there will be xn, yn, and then x capital N, y capital N. So when I train, I will train on n minus 1 points, leaving out 1 point. So then in that training, obviously my error will be like this in the validation set, leaving out 1 point, just 1 point, which we know as I'm writing the same thing, gn minus xn and yn. I just leave out this point and keep this point only 1 point for validation. N minus 1 point for training. And therefore, you know, the validation will give me this error. And what I do, what I call it as a cross validation error, I hope the term is now familiar to you, is the average of all En. That means I do this experiment n number of times, keeping 1 point at a time. First, I will do without this first point. Second time, I will do again without the second point. Third time, I will train again without the third point and try to make it cross validation error as this. And we call it as an ECV, cross validation. But see that the EMs are very much dependent on each other, because when I train without the first point, the third point was inside my training to give my hypothesis. My E3, when I remove the third point and keep it for validation, my first point was inside my training and will be part of governing my hypothesis. This will be absolutely very much dependent. However, taking an average makes it little bit smoother. And as we have seen, and you have also seen, such kind of a cross validation when you do with 1 point, it effectively gives you good performance and it lands up with the good estimation. Just one simple examples with the line fitting. Suppose if you understand this one, the cross validation is perfectly understood. Suppose I have 3 points. I want to fit a line. As you know, what I will do, let me ignore this point, try to fit a line. Sorry, my line is bad, but let me now switch up the point over it. Try to fit a line like this. So what is the error that I am making? I am making this much error. I mean, if the line is like this much error is the error of this point, E1. Next, the same way I will do. I have 3 points here, here, and here. I will try to fit a line with these two. So the error that I am making is this much, E2. There is cross validation. I'm just doing cross validation, separating out 1 point from my data set and trying to fit a line. So the third point is fitting a line like this, where this is the error. So now you can easily understand that what I will do now with my cross validation is just I will try to estimate my ECV is 1/3 of E1 plus E2 plus E3. Now, instead of a line as a model, suppose I am given with a constant to fit in as a model. So again, the same points. I am given a constant to fit in. So therefore, with respect to these 2 points, the constant line will be in the middle. And as you can understand, you will make this much error, E1. The second one, I am giving this, this, and this. I will try to fit in the point with these two. Sorry, this is not as like this. And you see the error I made here is almost null. I would say this is E2. And then again, I am given with 3 points, this, this, and this. And with respect to now, I made it with respect to these two, I made with respect to these two. Now with these 2 points, it's almost like this. And the error that I make is this, E3. So obviously in this example, as you can see, so this is my linear fitting and this is a constant fitting. And I will just try to check my cross validation. So as you can see, this is an hypothesis model 1. This is a hypothesis model 2, linear or constant. And depending on your cross validation, you may select that which one wins. So this is how you apply the cross validation. In practice, what we did is in practice, if you look at the digit recognition, if you remember the digit recognition example, so what we do in practice is that one-sided we plot symmetry for recognizing 1, and one-sided we plot intensity. And as you can see, for once, the symmetry is much more, but the intensity is less because the number of pixels that make 1 is very less. So the most of the data points will reside along this, apart from some aberrations, maybe 1-2 point like that. And other, let's say for 5 and all, the intensity is very much, but there is very less symmetry. Maybe 1 point could reside like this. And you will see the most of your 5 points will reside in this boundary. Now, if you try to go for cross validation, first of all, you need to check for many models. And as we have seen that this is a thing that is intensity and symmetry, these 3 attributes is not linearly separable. To apply certain linear things, we need to transform it into a different domain. So it may be x1, x2, x1 square, x1 square, x2, x2 square. All these parameters can come, and somewhere you need to cut through to make your smoothing going or make your early stopping going on. So you can see that without validation, if you run with this and this experiment, that without validation something it does like that, and maybe this it separates out, and maybe somewhere this it separates out. Sorry, not this one it separates out. Now with validation, so we can see that with validation, if we do this experiment, it does a very perfect job here like this, where without validation we find that the in sample is perfectly fitting, 0% error. The out of sample may have an error of 2.5% because the out of sample you do not know, these are the points that is given to you, maybe some error it will make. But with validation, the in sample, you might get a little bit of error in the in sample, since these points are in sample wrong when you make this blue shaped curve as your choice. But if drastically you save in the out of sample very much, and kind of a 40% improvement in this range. You make a 40% improvement in the out of sample. That's what validation does in practical sense. One final point before we finish. You not only use cross validation in your experiment, you also use this taking as 1 point for testing and the rest of n minus 1 point for training, and doing it for n number of times is computationally very inefficient. As you can understand, your n could be huge. n can be large. It is a million n we provide. Separating out 1 and 99,999 points as training this many times is very bad. So therefore, what we do, the full training data set, we divide it into equal clusters of data points. And then what we do, we just remove a cluster while training. So let's say this is my D1, this is my D2, this is my D3, and so on. This is my DK, and so on. This is my DN. I will train on DIs, all DIs minus DK. Validate on only DK. Then what you do, you repeat this n times. Sometimes this as your validation set, rest is training. Sometimes this as your validation set, rest is training. Sometimes this as your validation set, rest is training. And you have done this because this is basically what it does. It uses n by k training sessions, assuming that the length of this is capital K, each of these blocks. So it uses n by k training sessions, and each training session has n minus k points to train. This is simple mathematics, because if you remove k point, there are n minus k points to train, and you need to use n by k training sessions rather than n training sessions, which was earlier very bad. What is this called? You know it. Tell me the name of this approach.
Cross validation.
So
K-fold.
earlier was, yes.
K-fold.
Yes. Occasionally, what you do, you use this one, k-fold cross validation. Here, your k is, so suppose if I have this equal to 10, then it's a 10-fold cross validation. So if you can fold your data 10 times, separate out one, and have the 9 set as the training, and 9 set having those many points, and so the number of k determines that how many points you want to do. Okay, so this is called in general the k-fold cross validation, and that you extensively used in your projects. What is stratified cross validations that you do? Instead of picking up the samples from each of them uniformly, you build a strata out of this sample. As I have said, you have, this has some points like plus minus plus, this has some points like plus 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 minus and all that. You build a strata of points. Earlier I gave this example. You give a strata of minus points. Now each of this distribution, you create from this strata a new distribution of D1, D2, D3 like that. Purely statistical, but this is stratified approach of cross validation that you used also in your projects. So this is in a nutshell what we do in validation, and why theoretically validation is a good estimate, because it tries to estimate my out to a more better sense, because now I have two ways to do it. One, to train and find out the best during validation. I just click on the best and then put up all the validation data again into training set, get the estimate. If the k is less, then the estimate more somewhat matches very closely to the outcome that I provide to the customer. That's it. If you have any questions, then we can ask. Otherwise, I'm 2 minutes ahead of time. I mean, more than the time, not ahead.
So this we are doing only on training set, no? Test set is separate.
No, test set, you do not know the test set. See, someone gives you a problem. See, movie rating problem. What someone gives? Someone will only give you the, you will only see from the IMDb the existing user how they have rated it, right?
Yes, sir.
Now, some movie will come up tomorrow and they want to predict it. So you never know. rainfall prediction. You will only get the previous year's history of rainfalls. So depending on that, you segregate the data into a little bit of validation and mostly in the training, and then try to figure out all these types of approaches. Give the estimate on the overall data, give the eval of best hypothesis estimate as the proxy for E out. That's the deal.
Yes, sir. Suppose if we want to like check our model, so if we have a set of 100 elements, so we will like break it in 60 for 20 20, right? To
N by 5 usually. I mean, 80-20 is the best. I mean, people have experimentally done that. Somebody does it 70-30 also.
no, sir, like validation plus testing of the model also, if we want to do that.
No, testing, you do not have test points in your hand. You do not have test points in your hand. Na?
So
You only
like
have
the
data sets. You separate it out as training and validation.
no, so data set we can also separate it out as test also, no, sir?
No. That's what I said. It is not. It's a little contaminated because you are again putting it back to get your final hypothesis.
Okay.
So test set is not like that. I mean, test set is not again putting it back for getting the final hypothesis. Right?
Okay, sir.
So,
Yeah.
sir, I have a message from Suhas Chan, sir. He said that he won't be joining. He will not join today's meet, but he will write down the scripts.
Okay, fine. Thank you. Just tell him to follow it and then write it down.
Yeah, sure, sir.
Okay, so that's it. Let us stop recording.